Yes.
Yes? Okay. And if I change, does it change?
Yes. Yes.
All right, very good. So uh, I'm going to stop my video just to avoid any potential problems with that. So the work I'm speaking about is some recent work with Ben Green and Dimitris Kokolopoulos on the concentration of divisors. So it's a somewhat of an old problem. It goes back to work of Erdős. To set things up, and I should mention that Ram Murty gave a very good introduction to this in his talk yesterday. How are the prime factors of a random integer distributed? Well, from early work of Erdős and then later refined by Kubilius, if you look at the statistic which counts the prime factors in an interval, let's say e to the a to e to the b, that's roughly that statistic behaves like a Poisson random variable with parameter b minus a. And moreover, if you have independent intervals, these behave like independent Poisson variables. The underlying reason is essentially Merton's theorem. So if you take a random integer n and you take a prime p, what's the probability that p divides n? It should be about 1 over p. So if you sum that probability over an interval, you apply Merton's theorem, and you can see that normally you will have b minus a primes in such an interval. But that gives you the center of the distribution. The whole distribution is given by a Poisson random variable. So if b minus a is large, by the central limit theorem, this approaches a Gaussian distribution. But in the case that we're going to be looking at, b minus a will be rather small. So the distribution is more discrete. Divisors of integers, of course, are formed by taking all possible products of the prime factors. And it turns out that while prime factors are useful to be looked at on a log-log scale, the divisors are more useful to be looked at on a log scale. That's because if you have, let's say, k prime factors, there are 2 to the k divisors. So up below a number t, there are about log t prime factors, and therefore a power of logarithm divisors. Okay, this is very rough. Another way of looking at it is if you create this set, which I'll call d sub n, which is the set of the logarithms of all the divisors of n, you can express this as a sum set of all these 2 element sets. So this is in the language of additive combinatorics. So in other words, you obtain the divisors by taking all possible subset sums of the primes. So what motivates our work is this old conjecture of Erdős that says almost all integers have 2 very close divisors in this sense, that they are within a factor of 2 of each other. Now, this remained open for a very long time, although heuristically, Erdős had the following argument. If you take the difference set, dn minus dn, okay, that's the same as looking at all the logarithms of ratios of divisors, and by removing common factors, it suffices to look at co-prime divisors. And if you just count these, let's say n has k distinct prime factors, we'll ignore repeats for the moment. Then there'll be 3 to the k elements here, which is log n to the log 3. If k is, if the number is normal, it has about log n prime factors. And the key idea is that these are numbers in the interval negative log n to log n. and log 3 is bigger than 1. That's a numerical coincidence that drives a lot of the behavior in this area. Yeah, so that's a heuristic. It was extended to, okay, so here's Erdős's heuristic again. In the 1970s, Erdős and Hooley independently invented a concentration function called the delta function. So you take the maximum number of divisors in any interval of type e to the u to e to the u plus 1. So it's almost a dyadic interval. It's just convenient to use e instead of 2 here. So Erdős conjecture morally corresponds to the delta function being at least 2 for most n. Okay, and I just want to mention as an aside, there are many applications of the delta function, starting with Hooley's paper, motivated by Diophantine problems. Okay, so many people have worked on that, and there are different variants of the delta function, but I'm going to concentrate here on the original delta function. Okay, so here's the delta function again. A big breakthrough was made in '84 when Maier and Tenenbaum solved Erdős's conjecture, and they did even more by showing that the delta function for most n grows at least as large as a particular power of log n. Okay, so this particular constant here, this was refined by the same authors in 2009. A little bit better lower bound and also a corresponding upper bound, which is a power of log. The exponent here is log 2, which is about 0.7. So there's still a gap between the upper and lower bounds. Moreover, for various reasons related to the procedure that they developed, Maier and Tenenbaum conjectured that the lower bound was, in fact, the truth. Okay. So I want to briefly outline some of the methods, some of the highlights of the Maier-Tenenbaum work, because some of these will, of course, play a role in our new work as well. The first one was to focus on the prime factors of a random integer in a certain interval, y prime y, where y prime is given by this expression and c is a small constant. Okay. Then Erdős's conjecture also implies, his heuristic implies that the function I call dnj, which is the logarithm of divisors composed only of these primes, that will also have 2 close divisors. So to show this, Maier and Tenenbaum did 2 things. First, they proved that the difference set was nicely distributed in this interval. Okay, I'm being intentionally vague here. But what we care about, of course, is having an element near 0. That would correspond to 2 close divisors. Well, if there aren't 2 close divisors, then you can use a small number of larger primes to fill in the gap near 0. Okay, that was a really key idea in their paper. Again, I'm sweeping aside details at the moment. Another idea was now to apply the same argument to many disjoint intervals of the same type, right? So you'll have two close divisors in one, 2 close divisors in another, and since they involve disjoint sets of primes, you can glue them together in all sorts of ways, combine them, and then get a large number of divisors in a relatively short interval. Okay, so 1, 2, and 3 correspond to their 1984 paper. In 2009, they exploited what are called unused primes from one set to generate divisors from the prime factors in the next set. Again, I'm being a bit vague here. I'll make this more specific later. And that allowed them to deal with shorter intervals. Okay, so this theta is quite a bit larger than the C that comes up here. Okay. Now, what we did, incidentally, we originally were trying to prove the Maier-Tenenbaum conjecture. And in a way of doing that, we created a Poisson type model for the prime factors of an integer and realized pretty quickly that if we look at the prime factors in one of these intervals, which is the intervals that we care about in this problem, so that's roughly Poisson with parameter 1 over k. But since k, we're thinking of k as large, that's actually close to a Bernoulli random variable that takes only 0, 1 values. So a Poisson variable with a small parameter very rarely has the value 2 or larger. So we are considering then integers that have either 0 or 1 primes in such intervals. And we model that by a random subset, let's say of the integers up to capital N, where we choose the element to be in the set with probability 1 over k. So say this is a random, let's say harmonically weighted random subset of integers. So then the correspondence would be the set will correspond to the logarithms of the prime factors of a random integer. And then the delta function will correspond to a concentration function on the set A, which is simply the maximum concentration of the subset sums. So we take the maximum over n and we count how many subsets of our random set have sum equal to m. Okay. Now it's not an exact correspondence, but it's a relatively short argument to move from results about FA to results about the divisor function using, let's say, the Kubelius model. So just a quick example. If A is the set 1, 2, 4, 5, 7, okay, what is f of A? Just to clarify the concepts here. It's 3. So there are the maximum concentration of subset sums is 3. It occurs at both 7 and 12 by symmetry. So for example, 7 has these 3 representations as a sum of elements of A. So just 7 itself, 5, 2, and 4, 2, 1. Okay. All right. So what can we prove about this? So again, here's the setup. Each element of A corresponds to a logarithm of a prime, and sums of these correspond to logarithms of divisors. So our new theorem is that one of the theorems for this particular number here, the concentration function of our random set is larger than log n to this exponent with high probability. And as a corollary, we show that the delta function is greater than log n to the same exponent for almost all n. Okay, so in particular, we disprove the theorem, or sorry, the conjecture of Maier-Tenenbaum. So if you compare our exponent with the 0.338 exponent here, it is a little bit better. We have ourselves gone out on a limb and conjectured that our lower bound is the truth. And the reason for this is because we have created an entirely new framework for discussing an optimization problem related to this problem. Okay, so we have a whole new framework, a whole new structure, which I will spend quite a bit of time talking about. So a sub-problem, which is really the main problem of our paper, is the following, which is related to what I called idea number one from the Maier-Tenenbaum work. So we focus on the integers in our set lying in an interval of this type, okay, which corresponds to looking at divisors of a number composed only of prime factors from an interval. And we want, for a given k, we want to maximize the value of c. In other words, make the interval as short as possible so that we have a concentration, we have at least k equal subset sums with high probability. Right? So the theorem we show is that, okay, this corresponds to a lower bound on beta sub k. Right, so the beta sub k grows at least as fast as, let's say, k to the minus 1 over c. That's what's being written here. And so then, of course, we use the Maier-Tenenbaum idea to glue many disjoint intervals together, and that's how we obtain the theorem on the previous slide, this lower bound here with a certain exponent on log n. Okay, so going from this theorem to the previous theorem is not much of a mystery. All right, so again, what's the correspondence to actual integers and divisors? We're maximizing the c so that if we have an interval, what I call j here, and we look only at the prime factors from j, then with high probability, we can form many close divisors, so k of them. All right. So now we'll get kind of a summary here. Let me explain some previous work. So beta k is this restricted concentration problem. The value of beta k also, through our model, corresponds to the problem of finding k very close divisors in a very short interval of this type here. Okay, so this is much shorter than dyadic. So it corresponds to the problem of maximizing the constant alpha so that with high probability, a random integer will have k divisors in such an interval for some y. Okay, so one of the theorems we prove is that there's an upper bound on alpha k. Okay, again, we want to make alpha as large as possible here. Let me see. We actually conjecture equality here, but we are unable to prove that at the moment. There's something amiss here. I believe, sorry, this is the wrong, this typo here. Okay. Yeah. So it should be a lower bound. Sorry about that. Yeah, so there's a lower bound on alpha k. We want to prove that alpha k is somehow large. And we conjecture equality. So what was known before? Well, essentially from the Maier-Tenenbaum analysis, you can get an exact value of beta 2. In fact, what they proved was an exact value for alpha 2. So alpha 2 is this number involving the log 3, which is no real mystery where the log 3 comes from. For larger k, again, the Maier-Tenenbaum work implies these bounds. And now they're a little complicated. So the takeaway here is that the upper bound is something like 1 over k, and the lower bound is 1 over k cubed, roughly. Okay, so again, there's a rather large gap between those. Another takeaway from this is that the lower bounds are the same for every k between consecutive powers of 2. So in particular, Maier-Tenenbaum's lower bound for k equals 3 and k equals 4 are exactly the same. Okay, in other words, they did not know how to pack 3 close divisors in a short interval without doing it better than packing 4 divisors in a close interval. So that was another important sort of unsolved problem. So some of the work that, as a consequence of the work we did, and this did not appear in the long paper that we put on the archive. This is going to be future work. We have, in particular, exact values of beta 3 and beta 4, which are given by these expressions. Now there's a row 1 and row 2 appearing, which are given by these exact formulas here. Again, the log 3 is not mysterious, but this log 2 over e minus 1, that's a little harder to explain where that comes from. But so the point is, if you compare the lower bound of Maier-Tenenbaum in the case of beta 4, it was something like 1 over 86. So we have a larger value here. So that improves, immediately improves alpha 4. Another thing to notice is that we have a much better bound on alpha 3 than we do for alpha 4. And we conjecture that these are in fact the truth. So that's something I want to discuss in detail in just a moment. Also, as I mentioned before, when k is large, we get something like a lower bound of the size minus 1 over 0.3533, that specific number, which for large k, now that also improves the Maier-Tenenbaum results. Right, now to speak about how we arrived at these, and we have a procedure now to evaluate beta k for any k. And we set it up using some linear algebra and somehow isolating large elements, which I'll talk about in just a moment. So here's again, in green, this is the main problem we are dealing with. We want our random harmonically weighted set to have k equal subset sums with high probability and to maximize the C. All right, so suppose that we have those. Okay, so the subset sums will be capital A1 through capital AK. And what's important is to look at the complete Venn diagram for these k sets. Okay, that'll give 2 to the k pieces. And I'll denote by b sub omega those different pieces, where omega is now a subset of 1 through k, and it somehow indicates which sets we are intersecting. Okay. On the next slide, I'll start showing some pictures of this. Also, it is important to understand certain thresholds. So we have C1, C2, C3. It's this decreasing sequence of real numbers starting at 1. So somehow to optimize those, and also to optimize some what we call measures, mu r through mu 1. And all these are doing is counting what proportion of the integers of a that lie in this interval lie in each of the Venn diagram pieces. So mu sub j is supported on a set of size 2 to the k, and we want to optimize those numbers. So there's a certain procedure here for doing that. I'm not going to discuss the procedure just yet. I want to just show some pictures. Okay, so k equals 2 is the easiest case. So there we just want two equal subset sums. Okay, so what we want is, well, we want the sum A, let me write this here, A in A1 to be equal to the sum A in A2. And the Venn diagram has four components, but two of those components don't play a role here at all. So anything in the intersection can be dropped out of both sides. I should put an A here. Okay, so these play no role. And okay, so we don't care about what's in here, but the optimal choices, which were discovered by Maier-Tenenbaum, are 1/3, 1/3, and 1/3. Okay, what does that correspond to? Well, you have an integer, and you take a random, let's say you take a random divisor of that integer. Let's say the integer has m prime factors. So you take a divisor, and then you take another divisor at random, and you look at the Venn diagram, and then with high probability, you will have a third of the elements in one, a third of the elements in the other, and a third of the elements either in the intersection or outside. Let me see if I'm saying that right. Okay. The idea is if you have two divisors and you look at this is basically comes from the trinomial distribution. If you take m, choose a, b, c, it maximizes at a, b, c all being around m/3. Okay, but that's what it corresponds to. So it's a pretty easy explanation where the 1/3 comes from. But in some sense, what this means is that we're in this interval, we're using about 2/3 of the prime factors, and the other 1/3 are somehow unused. Okay, and Maier-Tenenbaum exploited that in their later work to, okay, which I've illustrated here in the case of k equals 4. So that corresponds to two intervals, two measures. Okay, the top measure is pretty well understood. We'll take 1/3 in this intersection, 1/3 in that intersection, somehow thinking of these two sets as being glued together, and 1/3 outside. But the interval C2 to C1 is much smaller than they had before. The interval C3 to C2 is exactly the same size they had before. It has a ratio. The ratio is 1 minus 1 over log 3. And it may be a little bit harder to read. I tried to cram this onto one slide. So there are also 1/3 of the divisors in each of these two intersective pieces, but then there's also 1/9 in these two. So the two 1/9 pieces here correspond to what was going on in up here. So that gives a way of, how to say, utilizing these extra divisors in a strategic way. These unused prime factors down here to build up a divisor from what we had in from these prime factors here. Now, what they did is they produced two close divisors from mu2 using the 1/3, 1/3 pieces, and then another pair coming from here and from here, and then glued them together in all possible ways to get 4. Okay. Another takeaway from this is that there's no way to modify this argument, the way it's set up here, to obtain just 3 close divisors in a short interval without doing 4. Okay, so this was optimized for powers of 2. Okay, you can do the same thing for 8 and 16 and so on. So our new analysis, let's say in the case k equals 3, now we want 3 equal subset sums, which I indicated by these three colored circles here, and I've created the full Venn diagram. We also have two intervals. The first one is actually very short. The ratio of C1 to C2 is something like 3. The ratio C2 to C3 is much larger. This is something corresponding to 1 minus 1 over log 3, but not exactly. It's slightly different. So on the upper set, we do exactly what we did before. We'll have our measure will be supported on 3 parts, 1/3, 1/3, 1/3. But the measure mu2 is the most complicated part. We're using every single piece of the Venn diagram except for the central part, which plays no role in the analysis. And here the number e comes up. We have, instead of 1/9, we have 1/3e here, here, and here. And then instead of, well, the same thing here, we have these 4 are e minus 1/4e, right? Now, where does this come from? It comes from a particular optimization procedure. Okay, so this measure here is provably the best choice. Mu1 is provably the best, and these 3 constants are provably the best. Okay, that's the point here. In k equals 4, we improved on the Maier-Tenenbaum estimates in k equals 4 as well. So that is trying to find 4 equal subset sums or 4 close divisors. And what's interesting here is now we have 3 measures instead of the 2 that were considered by Maier-Tenenbaum. And there's a funny thing going on with the middle one, because the interval from C3 to C2 is extremely short. It's a very tiny piece here, but it plays an important role. If you remove that, then you get slightly worse results. So yeah, the ratio here is about 1 to 7, and the ratio here to here is something like 1 to 11, which is, that log 3 minus 1 again. It's a little bit hard to put that all on one slide because we're using every piece of the Venn diagram, which that is all 16 pieces except for the full intersection piece. But there's also some linear algebra going on behind the scenes. Is that mu2 is supported on, okay, so if capital mega is we think of the Venn diagram pieces indexed by the discrete unit cube, then there's a certain subspace intersected with the Q where mu2 is supported, and a even smaller subspace where mu1 is supported. So mu1 is supported on these 4 pieces, and in fact has value 1/3, 1/3, and 1/3, with this part being 0. Okay, so I didn't draw that, but this hints that there's some interesting linear algebra going on behind the scenes. Okay, so our optimization procedure uncovered this. All right. So now things are going to get a little bit more technical. Again, remember we have these, our goal is to show that A1 through AK exist with high probability, that have this relation here. So what we're going to do is, given A1 through AK, we're going to build up some vector spaces. And the first vector space is the trivial one, which is spanned by the all one vector. And if you intersect that with omega, there's just 2 pieces, all ones and all zeros. And those, how to say, don't matter in here. So now we'll take the piece of the Venn diagram not in here that contains the largest element. So it's the largest element of any of these sets that actually matters. And yeah, okay. So it's the largest element of the union here that's involved in any of these. V1 will now be a vector space spanned by the all ones vector and omega 1. And from probabilistic heuristics, A1 will be roughly of size n for most of the time. All right, so then what we're going to do is something interesting. I'll take all the parts of the Venn diagram that are not in V1 and take the largest element, the piece omega 2 that has the largest element of what remains. Okay, this turns out to be important. And then C2 will simply be the size of that element. In general, C2 will be smaller than 1. We let V2 be the span of now these 3 vectors, the all ones, the omega 1 coming from step 2, and the omega 2. And we continue this way until we've exhausted everything. And then that produces our sequence. And it also produces what we call a flag of vector spaces that start with V0 and end with, let's say, Q to the K. Okay, we could have just said R to the K, but these are all rational, so stick with Q to the K. All right, so that's some linear algebra that comes out of the method by looking at these various subsums and taking various linear combinations of the different pieces. All right, now we're getting into some very technical points. So when we ran our upper bound and our lower bound for beta k, they both required us to look at something called the entropy of a subspace, okay, which is essentially you sum over all the cosets x, and this is the usual, how to say, entropy function. And we also wanted to look at what we called subflags. That turned out to be very important in the analysis. So it's just a flag of vector spaces where each Vj prime is a subspace of the Vj appearing on the previous slide. And we allow equality here. So we allow equality in some of these. So that's a little different from what people usually use the word flag to indicate. And now, again, this is a very technical condition. There's this certain expression, which is a function of the subflag and a function of these thresholds, Cj. Okay. And if we define gamma k to be the supremum of all constants such that there exists thresholds, measures, and a subflag with the following property, where the lowest value of the threshold, the lowest threshold is C, and we have this interesting entropy inequality, we call it. So the E function at these subflags is always greater than or equal to the E function of our original flag. Then I'm skipping over some technical things here. We almost have that beta k is equal to gamma k. That's one of the main results of the paper. Our upper bound was fine. We have beta k less than or equal to gamma k. That's good. But the lower bound, we need something called gamma k tilde, which requires for all proper subflags to have strict inequality here. It's a technical issue that we haven't found a good workaround for yet. But morally speaking, gamma k and gamma k tilde should be the same. So this we think is the truth, and we almost have a proof. Okay, so remember beta k was this constant where we if we restrict our set script A to be to have integers in a certain interval, then we'll get k equal subset sums. Okay, and that corresponds to k close divisors. Now, to explain where the special constant zeta comes from, well, now we have all this set up. We were considering very special flags of vector spaces, which have a great deal of structure. And in fact, here's a definition of that flag. It's a very compact definition, which hides a lot of the structure. But so we identify these indices. So again, k, we're specializing to powers of 2 again. That's kind of an important special case, just like Maier-Tenenbaum did. But we obtain better bounds than they did for every r, in fact. So we index things by subsets of r. Of course, there are 2 to the k possible subsets. And okay, so this is kind of a special definition. Then we're able to prove that the beta function or beta parameter with index 2 to the r is at least rho over 2 to the r, essentially, where rho is a very specific number. And after some long, difficult analysis, it turns out that it's the unique solution of a very messy looking transcendental equation. So we have now at the bottom, there's a recurrent sequence, but that recurrent sequence depends on rho. And then we plug that into this sum over here and then try to set equality. At first glance, it's not even obvious that rho should exist or be unique, but it is. And the main reason is because the terms in this sum are rapidly decreasing because of this 1 over 2 to the j. So this is a rapidly convergent sum here. Even though the a sub j's here are growing very rapidly, but we're taking a logarithm. So that nullifies the growth. Yeah. So that's again, there's a tremendous number of details being omitted here. So again, back to where we were. Yeah, so this is the new analysis. So again, this in the case k equals 3, there's essentially up to isomorphism only one flag to consider. So the optimization is very easy. Now, given a flag, which means essentially given how many of these mu's there are and what their support should be, we have a relatively straightforward procedure for optimizing the constants and the measures. And that involves some ideas from linear programming. Okay, but we do have some specific expressions for that. In this particular case, those expressions were very easy, and they led to the numbers that you see here. This 1 over 3e and e minus 1 over 4e. Those numbers pop out immediately from the analysis. Part of it comes from certain entropy inequalities, and since there's a natural logarithm in the entropy, maybe at a meta scale, it's not totally surprising that E should be appearing in the optimal answers. In general, the measures are not so easy to write down. All right, so I think I will stop here. So I guess we can have questions or.
Yeah. So thank you very much, Kevin. It was really wonderful talk. And so questions are welcome. Remarks. Uh-huh. Well, okay, you were too clear. So thank you again.
Yeah.
And so I am thanking both speakers for this afternoon session. And so we'll resume tomorrow morning. Okay. Good night, everybody.
Okay. Good night. Thanks again for inviting me to speak. Yeah.
Thank you,
Okay, there is
everyone.
something from the organizers.
Yes, thank you, everyone,
Okay.
especially
You are
the
now.
chair.
I am out.
I think Anirbandha will take over. Anirbandha, you have to announce for tomorrow's thing.
Yeah, if you would like to post my slides somewhere, I'm okay with that. I don't
Yeah,
know.
sure. If you could share, that will be very nice.
Yeah, I believe I sent them already to Sanali.
Yes.
So,
Okay.
yeah.
So
Also, your video recording, are you okay to post it on our IMSC YouTube channel? Actually, we are asking.
Sure. Yeah, that's fine. Although, of course, there's no video of me, just the talk, but it's fine. Yeah.
Thank you.
Yeah.
So we resume tomorrow afternoon.
And there is a change in the link in the morning session. There will be a change because there was a mistake. You have to announce that.
Okay. Yeah. So, but you are going to send the new link, right?
Yes.
Yeah. So there will be new link for the morning session. So earlier we have sent 3 links for all the days, but now we change the morning session link.
We'll still have 3
every
links.
day morning session is changing.